So earlier I'd suggested we might not actually be doing the problem with off the center of a loop. Let's go ahead and do that anyway. Let's say we're some here distance z above the center. That's r. Okay, and I want to know what the magnetic field up there. Now, if we assume that the current is going this way, then that would mean that the magnetic field in the center is going to be upwards. So you'd suspect it's going to be upwards up here. Okay, right hand rule, you put your thumb in the direction of the current, so some little ds over here is going to have a magnetic field that way. Some little ds over here is going to have a magnetic field that way. And so, yeah, the left and right components cancel. All right, so we know that dB, okay, again, this is like that, so that's Z, we'll say that's capital R, so here's R. dB equals mu naught over 4 pi I ds cross r hat over r squared. So this would be, because the ds and the r are perpendicular to each other, this would be mu naught I ds over 4 pi r squared. Now that's going to be the magnitude of it right there. And so, but that's going to be the total dB. But we know that what we really want is just the component there. Okay, so we want the vertical component. Okay, so that would be the cosine of that angle phi. Well, that angle phi is going to be equal to this angle right here. So we want the cosine of phi. Cosine of phi is going to be r over r. And so that means that we can then say that this is just the total dB. So we need cosine phi to be just that part that we're interested in. So the actual dB is going to be mu naught I r ds over 4 pi r cubed. Now, what is r? R is the square root of z squared plus r squared. So dB is going to be 4 pi I times r over, that is mu naught I r over 4 pi times r cubed. Okay, ds. So now we got to just do the integral. Now here's the nice thing. When we do the integral for b, everything comes out except for that. Okay, and so that's going to be IR over 4 pi r squared. So s is the distance around, which is 2 pi r. Okay, and so the pi's cancel. Okay, and so that's going to be mu naught I r squared over 2, so it's r cubed. Okay. So we then say that the b, which is only in the z direction, so this is only in the z direction, so this is going to be equal to mu naught I r squared over 2 r squared plus z squared to the 3/2. Okay. Now, as z gets really, really big, then we take a limit here, and that's going to be in the z direction. When you take the limit as that happens, then what happens is that the b goes to mu naught I r squared over 2 z cubed. Well, notice that is a dipole field because it's going as z cubed. Okay, so that's going to be a reminiscent of the electric dipole. So again, this suggests once again that here we've got this loop. Okay, so if the current is going around this way, like that, then the magnetic field is going to be going this way. And that looks just like the, aside from the part in the middle here, the external part looks exactly like the electric field if you had 2-point charges, a minus Q and a Q. Okay. And so again, this suggests that there is in fact a dipole, a magnetic dipole, in which we have a north and south end of a magnet right here. Now, this turns out to be kind of a fascinating concept too, because notice that in this case, we had an electric dipole. We literally had 2 poles. In this case, the magnetic fields are continuous. They're not really stopping and starting anywhere. And yet we have magnetic fields, and we have a magnetic dipole field without actually having individual magnetic poles. Now, we'll get back to that later, because it turns out there are no individual magnetic poles. You always have a dipole, but you never have a monopole, which would be a single magnetic charge.